Andrea Continella from Politecnico di Milano will present to us on obfuscation-resilient privacy leak detection for mobile applications through differential analysis. Andrea, take it away.
Thank you for the introduction. So I'm Andrea Continella. I'm a PhD student in Politecnico di Milano. And this is a joint work between Politecnico di Milano and UCSB. So as we all know, mobile apps are notorious for collecting and leaking a lot of private information. So, for example, IMEI, locations, and contacts. And this problem has been studied by researchers that propose approach to detect these leaks. And traditionally, these approaches are based on static or dynamic taint analysis. However, these approaches have strong limitations. In fact, for example, static taint analysis can be defeated by obfuscating the app, or dynamic taint analysis can be defeated by interrupting the flow between a source and the network sink, for example, also using native codes. Thus, researchers proposed recently a new approach that is analyzing the apps from the network perspective. So the main idea, the intuition behind this is that no matter how the applications are obfuscated, the leaked values have to be in the network. But identifying these leaks is not that easy. In fact, as this example shows, previous tools that have been developed to monitor the network activity are not able to handle encryption and obfuscation techniques. And also, this snippet of code shows, based on a real case, an application that first get the Android ID, then hash it, and source the hash with a randomly generated key. And then the result is encoded in base 64, and then it's sent together with the key to a remote server. And to address the limitation, we propose an approach that identifies privacy leaks in a way that is resilient to this kind of obfuscation techniques. And the basic idea is to perform black box differential analysis. So we first run the applications and establish a baseline of the network behavior. And then we modify the values of these sources of private information, and we run the applications again, and we are able to detect leaks, observing the differences in the network traffic. So, for example, in this case, we give an app a certain IMEI code, and we observe the network traffic. Then we change the input, and we see that the actual the outgoing request changes. However, performing black box differential analysis on the network traffic is not that easy. In fact, network traffic contains a lot of non-determinism. And this means that the output changes even if we don't change any input. So as a consequence, we cannot pin a specific change in the input to a change in the output to a specific change in the input. And this would make the differential analysis fail. But the key point of our research is that we found that this non-determinism can be often explained and removed, so making the differential analysis possible. And to address this non-determinism, we performed a small-scale study on 15 applications, and we identified 6 sources of non-determinism that are random values, so for example, random numbers or session identifiers. Then we have timestamps and dates. Values coming from the network, so for example, server-assigned identifiers and cookies. System values, so values about the state of the system, for example, the available storage of the amount of free memory. Encryption that uses random initialization vectors. And we also have non-deterministic executions that, since different loading times, might affect the UI exploration. And to handle this non-determinism, we leverage what we call contextual information. That is, in practice, we instrumented the environment in which we run the application in order to be able to record and replace non-deterministic values that are generated at runtime. So specifically, we record timestamps generated during the first run, and then we are able to replay these values during further runs. We also record random identifiers and plaintext and ciphertext during encryption. So in this way, we are able to map the ciphertext back to the plaintext. And we also set fixed seed for all the random number generation functions. And we set values of performance measures, so for example, the available storage to constants. And leveraging this contextual information, we build what we call a contextualized trace. that is basically a merge between this contextual information and the network traces. So in this example, we have in our network trace 3 requests, and we also collected some contextual information. And thanks to this data, we are able to decrypt encrypted content. Then we can also identify and label timestamps and identify and label random identifiers. So in this way, we can explain this non-determinism. So, OK, based on all these ideas, we build a system that we call Agrigento that works in 2 phases. In the first phase, we build a baseline of the network behavior of the application. So we run the application the first time, and we collect the contextual information, the contextualized trace. And then we run the application multiple times in order to include all these slightly different execution paths. So in order to have a more complete picture of the network behavior that we call the network behavior summary. Finally, in a second phase, we run the application again, but this time we modify the values of the sources of private information. We collect again the contextualized trace, and we perform the differential analysis with the network behavior summary that we previously built. This will produce the differences that we detect caused by the changes in the input. And finally, we estimate the amount of information that each of these differences include in terms of number of bits in order to be able to rank leaks according to their risk. And this is important to notice that we use a conservative and fail-safe approach. That means that we flag anything that we cannot explain. So even when we fail, so there is some kind of non-determinism that we cannot explain, our tool will raise an alert and will consider the difference as a potential leak. So in this case, everything that we cannot explain will result in a false positive, but not in a false negative. So another feature of Agrigento, an interesting feature, is that it automatically determines the number of times a certain application should be executed. And to do this, we perform the differential analysis at each step, after each run, without any modifications of the sources. And we say that an app reaches convergence when we don't see any difference in the network traffic for k consecutive ticks, for k consecutive runs. And in this case, when this happens, it means that we are ready for the final phase of our approach. So this picture shows an high-level overview of the architecture of our system. We use expose to instrument the environment in which we run the application and to collect the contextual information. And we also have a proxy that, using a custom certificate, is able to capture the HTTP and HTTPS traffic generated by the application. Finally, the main core of Agrigento is able to perform the differential analysis and produce the identified leaks. So to evaluate Agrigento, we set up an environment with 6 Nexus 5 running Android 4.4. And we let each app execute for 10 minutes. And we use Monkey for UI stimulation using a fixed seed. And we obtain a dataset of more than, in total, 100,000 applications. So we have 100, the top most popular free apps from Google Play, then 100 randomly selected less popular apps. And we also obtain access to the datasets of 2 related works, 750 apps from Recon, that is a tool that performs network flow analysis to identify leaks, and also 54 apps from Bayes-Droid that is based on Bayesian reasoning on the values observed in the network traffic. So as a first experiment, we measured the non-determinism in the network traffic. So we used the 100 apps from the Google Play, and we analyzed those apps twice. The first time, leveraging our full approach, so leveraging the contextual information. And the second time, by applying the trivial differential analysis without explaining the non-determinism. And in both cases, we performed the differential analysis without changing the values of the sources of private information. And you can see in this chart that even increasing the number of runs, the trivial differential analysis cannot handle the non-determinism. And in fact, more than 80% of the application actually showed some kind of non-determinism in the network traffic. While using our approach, we were able to handle the majority of these cases. Then we compared our tool to existing tools. And first, we used the Recon dataset, and we compared our result to the results from Recon's paper. And we saw that Agrigento detected many more apps than the previous tools. However, when comparing approaches that are based on dynamic analysis, the UI stimulation can actually affect the results. So we asked the Recon authors to run their tool on our network traces that we collected during the experiments. And we found out that Agrigento detected all the apps detected by Recon, and in addition detected also 49 new applications. We manually verified that at least 32 of these applications of the new detection were actually true positives. We also did the same thing with the Basedroid, comparing to Basedroid using the Basedroid dataset. So we found out that Agrigento detected more apps. And among these new detections, most of them were using, in fact, some kind of encryption or obfuscation technique. And I will show you an example in a minute. And finally, we also ran our tool on the top 100 apps from the Google Play Store, and we manually verified the results and classified the leaks in 3 groups. So leaks occurring in plaintext, leaks in which the leaked value has been encrypted using the Android APIs, or obfuscated leaks. And we performed this evaluation at 2 different granularities, at the app level or looking at each source of private information individually. And Agrigento identified 46 applications, and we manually verified that actually 42 were indeed true positives. And as you can see in this table, there is a good amount of applications that are using some sort of encryption or obfuscation technique to hide their leaks. All right, so this is one of the case studies that we identified during our evaluation. This request was flagged by our tool. As you can see, it's an unreadable blob of data. But reversing the application, we found out that this request was performed by a known library, ThreatMetrix, that leaks the IMEI code, the location, and the MAC address, storing these values with a randomly generated key. And then the results, the stored values, are encoded in a hexadecimal format. And finally, both the obfuscated values and the random keys are sent over the network. OK, so limitations. Our tool, as all the approaches that are based on dynamic analysis, suffer from limited code coverage. And we also suffer from coverage channel attacks. So, for example, an attacker that leaks information in the number of times a certain request is performed could evade this tool. However, this could be mitigated by adapting our models and considering also, for example, the number of times each request is performed. And also, we do not instrument native code, but that means that we cannot handle non-determinism generated by native code, but this will result, in the worst case, in a false positive and not in a false negative. Also, we only limited our study to HTTP and HTTPS get and post requests. And as a future work, we would like to investigate the malicious intents behind this obfuscation. And I mean, in this context, I think the next paper in this session will cover an interesting aspect, that is verifying if applications are respecting the privacy policies. So in conclusion, we found that non-determinism in network traffic can be often explained and removed. And we leverage this finding to build a system, Agrigento, that is able to detect privacy leaks in a black box obfuscation-resilient way. And we also found out from our experiments that there are apps and libraries that hide their information leaks using obfuscation techniques. Finally, we made our source code and the datasets available. So here's the link to the GitHub page where you can find the source code. And that's it. Thank you, and I'd be happy to take questions.